Amitha, and today we'll cover the rate law and reaction order. First, we'll discuss how to find the rate law from experimental data and reaction mechanisms. Then we'll look at the properties of each type of rate law, including their integrated rate law.
So the fundamental rate law for this reaction is rate is equal to K, the rate constant, times the concentration of A raised to the M power times the concentration of B raised to the N power. Reaction orders can't be found from the balance equation alone. They have to be calculated experimentally or using a reaction mechanism. So zero order reactions are not affected by the concentration. But if you doubled or tripled the concentration of that reactant, the reaction would proceed at the same rate as with the original concentration. For first order, if you double the concentration of the reactant, the rate doubles as well. For a second order reaction, doubling the concentration of the reactant quadruples the rate. So to find the overall rate of the reaction, you add the exponents for all of the orders of the reactants. So that would be overall is equal to m plus n for this reaction.
Reaction is zero order. The unit of K is molarity per second. For first order reactions, the unit of K is 1 over seconds, and for second order reactions, the unit of K is 1 over molarity times seconds. Zero order reactions have a rate law of rate equals K, and first order reactions have rate laws where rate equals K times the concentration of the reactant. In a first order reaction, the rate constant is equal to 1 over seconds. Notice that this differs from a zero order reaction. We'll discuss why that is and how you can find K later. In the chart shown, when the concentration of A increases, the rate does not change. So when here you double the concentration, the rate stays the same, which makes A zero order because there is no correlation. But when you increase the concentration of B, when you double it by 2, the rate is also doubled by 2. And since the magnitudes are the same, this is doubled and that's doubled, it's first order with respect to B.
We can also use a reaction mechanism to determine the rate law. A reaction mechanism is the list of elementary steps that will add up to the total reaction. The total reaction can't be faster than the slowest step. So when given a mechanism, you can find the rate law using the coefficients of the reactants of the slowest elementary step. So for example, for this reaction, we have these two elementary steps right here. Since the slowest step is the second step, we know that the coefficients of this step will help us to find the rate law. But because D is an intermediate and not a reactant, we can't have that in the final rate law. But since this fast step is in equilibrium, some of D is always going to be converted to A plus B. So we can replace D over here with A plus B. So the reaction essentially over here is kind of like A plus B plus B. So when we come to our final rate, we see that we have one A, so the coefficient of A is 1, and then we have two B's. So B is second order. And that is the overall, that is the reaction order for this mechanism. So although in this case, the reaction, the coefficients of the rate law are the same as the coefficients of the initial reaction, we can't always assume that that's going to be the case. So we have to always go through with the steps of either using experimental data or either using a reaction mechanism. Once again, in order to make sure, you have to always use the elementary steps or the other types of experimental data.
In experiment 1 to 3, the concentration of NO doubles and the rate quadruples. So we could say that. And then the reaction is second order with respect to NO. But for Cl2, from experiments 1 to 2, the concentration doubles and so does the rate, which means that the reaction is first order with respect to Cl2. So our final rate law is rate times K times NO squared times Cl to the first power. Overall order of the reaction is 3.
So depending on the order of the reaction as a whole, the units of K will differ. Finding the unit of K is an integral part of the AP exam. It's important to remember that the units of K multiplied by the units of concentration should always equal concentration over time, or the unit for the rate. To find the numerical value of K, you can use this formula. So the formula is K is equal to rate over concentration of the reactant. So in this case, concentration of A to the 5th and B b to the second, because that's our reaction order. So here's a quick practice problem up here. Pause the video and resume when you're ready for answers. So once we plug in our values into the derived formula, we get that 17 mol per minute over these values over here is ultimately equal to 3.1 times 10 to the negative 4th mol over all these units over here. So in order to get to the final answer, you need to simplify the units. So since we have 7 mol on the bottom and 1 up here, we can get m raised to the negative 6th power, and then we get minutes to the negative 1 power. And once you substitute that into the equation, anytime you try to solve the problem using various concentrations, you'll always get the rate law, which has a rate with the units mol per minute. So to include, the most common reaction orders are first, second, and zero. For a first order reaction or reactant, the magnitude by which the concentration increases is equal to the magnitude by which the rate increases. For a second order reaction, it's the magnitude by which the rate increases is the square of the concentration increase. And for a zero order, any change in concentration doesn't impact the rate. So the only way to find the reaction order or reaction rate law is to use empirical data or a reaction mechanism. You can't just look at the balanced equation itself. And finally, when you have all of your orders for each individual reactant, the overall order of that reaction is equal to all of those orders. So in the case of our earlier example, adding the exponent of A and the exponent of B would equal the overall order. Finally, to find K, or the rate constant, you have to divide the rate by the reactants raised to their respective orders, and you always have to make sure that ultimately K multiplied by the reactants to their powers will equal the rate times a unit of mol per minute, or any type of reaction, any type of concentration over time.
Here's a practice problem using reaction mechanisms to find rate laws. First, find the rate law for this reaction, then consider the table independent of the above reaction mechanisms, and find the new rate law. What is the K and the overall order for this reaction? So the answers are that the rate equals K times HBr times O2, which you get from looking at the slow reaction. And then this is derived from the experimental data given, because HBr magnitudes are 2 to 2, and O2 magnitudes are 2 to 4, since the rate is quadrupled. The overall order is 1 plus 2, so it's 3, and then this is derived from plugging in sample concentrations from any experiment. This was experiment 3, and solving for K.
This production is made possible by viewers like you. Thank you.